Good morning, respected jury member, honorary chief guest, and my dear fellow mates. Today we are going to talk about wind energy, a practical power analysis approach. Now, why wind energy? Because wind energy and wind turbines have been used theoretically a lot, but the practical analysis for wind does not exist as of great importance as in theory as of today. So we are going to shed some light on the practical power analysis part more. So briefly talking about what we'll have the discussion about. So we'll introduce how wind power is actually generated. We'll talk about the future of wind power and its development and progress. We'll talk that why we have used wind energy and the assets of wind. Then we'll deep dive into the mathematical part of the wind speed distribution, which is the Weibull distribution, and then we are going to talk about the wind energy generation methodologies. Then we'll talk a little about the limitations of wind, which is given mathematically by the Betz law and the Betz limit. Then we'll propose our own equations and compare and contrast with the theoretical equations. Then we'll go into the mathematical modeling and the most important visualization part. Then finally we'll calculate the loss percentage and do use case for India. So, introduction. Till this very date, a lot of theory exists towards using the wind resources, but none of them are uh, able to shed light on the practicality of wind power analysis. So, what we are trying to do is we are trying to suggest an empirical equation which we've derived from machine learning technology, and we've used this to analyze data over a wind turbine in Turkey. That's where the data came from, and we've analyzed that actually. So, the practical behavior is not displayed in the theoretical mathematical equations that exist as of now, but we are trying to do that, and we are also going to do the loss approximation that we will see in the upcoming slides. So, why wind first of all? Why not any other energy source? So, as we know that the coal, oil, and gas will eventually get depleted as their non-renewable sources of energy, and it is postulated that till 2051, these resources will almost get depleted and we will have a problem at that time. So, so the future of wind power lies in its history too. Over the past 2 decades, it has enormously increased by a factor of almost 75. So, it is the future of power grids and it will provide global electricity. And that's there's a graph that shows this graph we can see is quite exponential, and we have predicted that around 2025 the global capacity of wind will reach to 1202.1 gigawatts. So that's a lot of power comparing to the 6.1 that it originally progressed from in 1996. So why wind energy? Because it's eco-friendly and toxic. It's renewable. It's clean and naturally available, and it control systems with modern technology. The wind turbines are, the wind farms and the wind turbines are all modern tech. They give a good amount of efficiency, and they're from natural resources, and they're feasible and economical. So how is wind originally generated? So uh, it is due to the irregular warming of the sun, global aberrations and anomalies in the surface, and the Earth's rotation. So, how exactly is wind converted? So, the rotor that we know is the wind turbine, of course, and then it moves some gears inside, known as the gearbox in general, and it goes into the generator to produce some electricity via some power converters, power transformers, and then it goes to the load to transmit the power. This is the an overall generalized overview of how wind energy is generated. So there are two types of wind turbines: horizontal axis wind turbines and vertical axis wind turbines. The basic difference lies in the horizontal and the vertical axes, and as you can see, the turbines are described in here. Now jumping into the mathematical part, the Weibull distribution is a sort of probability distribution that can define how a random variable looks like. So there are two parameters to the Weibull distribution, which is the shape parameter and the scale parameter. So this is the equation defining the Weibull distribution. And we actually, what we did is we took the plot from the Turkey data and we just plotted it. So this uniquely does follow a Weibull distribution, although with some deviation. So this is the actual distribution that we have, the red one, and the theoretical Weibull distribution is shown in green. So it's quite similar, and it does follow a Weibull distribution, in fact, and there's a slight deviation, but we'll jump into the details later. So what is the Betts law? The Betts law is the instantaneous equation for the theoretical wind power. So it defines what the wind power uh, at a instantaneous value is. So at t equals to say 1 second, what the wind power is. So this is a complicated equation that you can see, but if we differentiate it with respect to v2 by v1, which is এখানে description-টা বসাতে হবে, so which is the velocity upstream and the velocity downstream of the wind turbine. So if we get this and we differentiate it, then we'll get a simplified maximum theoretical wind power value, which is half rho s v cube t, where rho is the density of the wind there, s is the surface area of the turbines, and v is the velocity by which wind is flowing. Now uh, the velocity of the wind flowing is an average of the upstream and downstream thrusts of the wind. So here the derivation is done and the maximum wind power is calculated actually. So the Cp is the coefficient of performance, and it's also known as the Betts limit, that wind power production can never be more than 59.3% efficiency, which is also called the Betts limit. So that is good to know. But even as it is a renewable resource, even 59.3% conversion is not bad, and it gives a very very high output as when it is subject to like places like Gujarat, which are quite windy in nature. So this improved equation comes from a theoretical paper, which is half Cp Ng rho s v cube. So you can see that two different terms were introduced, which are Ng and Nb, which are generator efficiency and gearbox efficiency, gearbox bearing efficiency. So that is the improved equation. So now what we've done is we've actually thrown the equation into a linear combination, which is alpha into p theoretical plus beta into v square t. So why we did this is that we applied polynomial lasso regression over it, and these are the values we obtained for alpha and beta, and the dimensions are given. So what is the actual idea here? What are we planning to do? We are planning to superimpose, like, make it stick together, the calculated regression power and the actual power curve. So the curve that we obtain, it gives a good approximation for Vt less than 20 meter per second. Let me just go here. So as you can see that till 20 meter per second, it's a very very good approximation that we are obtaining from our derived empirical equation. And after 20 meter per second, it almost follows the theoretical equation. The green one is the equation that we got from the regression values, and the orange, or the rather the red one, is the actual power curve, and the blue one is the theoretical power curve. So the goal here was to stick close the green and the orange one as close as possible to get a good approximation of the empirical formula. Now calculating the loss, we'll take the theoretical value and the practical value and just do some mathematics over it. So we've taken the theoretical value and practical value, and we've just put it into this equation, and the loss percent comes out to be this equation. And now here you can see that the v square and the v cube term goes off, hence we are left with vt. Now beta is a very very small value that we know of. Beta was 0.7172. So beta itself is small, CP is greater than 1, NG will be around 0.91, and NB will be also around 0.91. Like high efficiency, almost 1. Coefficient of performance will be 53.7%. Rho SVT, these terms will be close to 0 and can be negligible, and hence we get the loss percentage as 1 minus alpha. So it's 9.87%. So that is the loss, like it's a constant loss that we're getting through the wind power calculation. So it is very very similar to the beds limit, but except we are doing it for a calculation point of view through a empirical formula based approach. So, wind power potential in India can be measured on a basis of three height levels: 50 meter, 80 meter, and 100 meter. And we did an analysis on various data from websites, and we got this approach that Gujarat definitely is the leading in wind power potential, followed by Karnataka and Andhra Pradesh, as is clear from the plot. So, if exploited in its full entirety, our country would be eligible for at least 60 gigawatt of energy each. Each state could contribute to 60 gigawatts of energy, like all the top three states. So, we could possibly produce at least 180 gigawatts of energy. So, that's a lot of energy. And in the rural and urban uses that we can talk about in India, uh, wind power can be used to for pumping water to rural areas, and it can generate electricity, so it can pretty much do pumping into local large coastal areas, hills, and desert stations. It can also propel sailboats for rivers and seas for proper transportation. It can grind grains in flour mills, and so on and so forth. There are a lot of things. So the conclusion that I want to arrive at is that this study is going to provide like a practical wind data approach, and how exists a lot of theory on wind, but there's no practical analysis. That's what we've tried to do here. We have also introduced a new parameter of how measuring how the wind loss is established, and from where these concepts come from are from the losses and the frictional force and a lot of other things. And thank you. That's my team, and that's all. So I was at 13 minutes. Right. Good.